Good morning, everyone, and I would first like to thank Lydéric for inviting me to this workshop and also for accepting a talk that will not be about flows. But I will discuss fluids confined down to the nanoscale and the physical chemistry of solid-liquid interfaces, and specifically the interface between a solid metal and a liquid, various liquids, but mainly electrolytes, and also like dipolar fluids like water. And in this presentation, I will show you some results and insights that you can gain using classical molecular dynamics simulations. So we're switching to simulations from Misha's experimental talk. And I'll get back to why classical molecular dynamics simulations, what they are. But we are trying to introduce some elements of the electronic response of the metal into these simulations in order to capture their effects on the interfacial structure, dynamics, and thermodynamics. So you can find fluids confined between metallic walls in many contexts, and obviously, for example, for lubrication, but this is not specific to metals, even though the friction will depend on the details of the interactions of the fluid with the walls, and so there the metallicity of the walls matters. But usually why you want to use metal is because you are able to control their potential, which allows you to store charge at the interface or even transfer charge at the interface. And this can be used, for example, in nanofluidique devices where you put electrodes on the wall. So these are experiments done by in Serge Lemai's group in the Netherlands, where they use the fluctuations of the current between two electrodes to detect the presence of redox active species. And you can infer properties on the interfacial fluid from the fluctuations of the electric current that you can measure with electrodes. And if you use two pairs of electrodes, you can also detect the presence of the redox active species between the first pair and the second pair, and using the delay between the two, you can also access the flow rate and so measure ultra-low flow rates in these nanofluidic devices. Now the main applications that you can think of with electrodes and electrolytes is energy storage in batteries where you do have redox reactions, and in capacitors or supercapacitors where you don't. And typically, batteries and electrolytes work with two metallic electrodes, which are separated by some medium. So in conventional capacitors, you have a dielectric medium, which could be solid or liquid. And what you want is to know how much charge you can accumulate on both electrodes, so opposite charges on the two sides, when you apply some voltage, so the potential difference between the two electrodes. And for the conventional capacitors, the capacitance, which is a derivative of the charge with respect to voltage, is given by the area, so it's proportional to the area, inversely proportional to the distance between the two electrodes, and it depends on the properties of the dielectric medium, namely its permittivity. In a supercapacitor, you replace the dielectric medium by an electrolyte, so you conduct electricity with the transport of ions between the two electrodes, and charge can be accumulated on both walls, so electronic charge can be accumulated by the excess of charge in the liquid on both interfaces, and the excess charge comes from the accumulation and depletion of ions on either side. I'm going to show you some results based on classical molecular dynamics simulations. So as an introduction, I also wanted to give you an overview of the variety of interfaces that have already been studied with this type of techniques. But probably I should also say just a few words about what molecular simulations are. And so the idea is to do a computer experiments in which you model the interactions between the constituents of your system. So it could be ions, it could be water molecules, it could be electrode atoms, here hydrophobic molecules, or more complex electrolytes. And you want to predict the trajectory of these water molecules and the ions in your system. And in order to do that, you simply solve Newton's equation of motion numerically. And in order to do that, you need a model of the forces that are experienced by your atoms. You can compute these forces based on an electronic structure description. So in ab initio molecular dynamics, you will have a computation of the electronic density for each configuration of your system, And from that, you will compute the forces acting on the atoms, which you can then propagate. In classical molecular dynamics simulations, you don't do this accurate calculation of the forces, but you rely on a model which is called the force field. And the quality of your prediction, of course, depends on the quality of your model, so the force field. But let's assume we have good models. Then you can use this representation of forces to generate trajectories, and then you can sample properties of your system, like the position of your atoms, the energy, and so on, and from that you can deduce observables like density profiles for all your species, the diffusion coefficients, and so on. So here are some examples. Here is a study of the ion pair formation and dissociation at platinum water interface by David Limmer and Adam Willard. Here is a study of the adsorption of hydrophobes at the gold water interface by Simone Pezzotti. And there they were interested in how the thermodynamics of the adsorption depends on the interplay between the hydrophobic solvation and the structure of the adsorbed water. In the context of energy storage, we modeled supercapacitors based on graphite electrodes with an applied potential difference, separated by, for example, ionic liquids. So this is an example that I'll get back to with butyl methyl imidazolium cations and hexafluorophosphate anions, using a coarse-grained model at the time, but now with the increase of computational resources, we can use a more elaborate model of electrolytes and model more complex electrolytes, like these water and salt electrolytes that are interesting in terms of energy storage because they have a wider electrochemical window. One thing that I'm not going to discuss in detail, but that is important, is that electrodes are not always flat, and in particular, in many applications, in particular supercapacitors, or also more recent applications for blue energy harvesting or desalination, you use porous carbon electrodes, and in this context, molecular simulations have also been used to understand what happens in nanoporous carbon electrodes, and there the molecular details matter, so the size of the ions and how they are correlated or not with the pore size in the material. So this plays an important role, but I'm not going to describe that. If you're interested, you can look at the article we wrote at the contribution in this issue of Chemical Reviews on Computational Electrochemistry, which contains a lot of interesting articles. Another aspect that I'm going to discuss in the second part of my talk is that electrodes are not always perfect metals. And to illustrate that, I'm going to use one of Lyderic's work, in which they investigated the capillary freezing of ionic liquids, which is related to interfacial thermodynamics. And in these experiments, they used the tip of an AFM probe to confine an ionic liquid between the tip of the probe and a substrate. And as they approach the tip, they observe a change in the mechanical response of the fluids from a liquid-like behavior to a solid-like behavior, which can be interpreted as capillary freezing, and the distance at which this capillary freezing occurs depends on the nature of the substrate, and they could show that the results can be rationalized if you consider various substrates that are more or less metallic. This capillary freezing distance can be rationalized in terms of the screening of the electrostatic potential and the charge distribution inside the metal via the so-called Thomas Fermi screening length, which is the inverse of this KTF parameter here. And so I'll get back to that point later on, but the idea is that the electronic structure of the metal has an influence on the interfacial thermodynamics. So from the modeling point of view, the standard description of charged solid-liquid interfaces is that of an electric double layer. So you have a layer of charges inside the solid and a layer of charge in the liquid that compensates that of the solid. And the canonical description that is already a century old is the Poisson-Boltzmann or the Bi-Huckel theory. It's based on point-like ions in an implicit solvent. You only consider electrostatic interactions and treat them at the mean field level. You consider a smooth surface, a perfect metal, and so on. In addition, you consider small potential differences. You can linearize Poisson-Boltzmann theory to get the Bi-Huckel theory, which predicts an exponential decay of the potential and the ionic density profiles as you move away from the surface. And the characteristic distance for this decay is called the Debye screening length, which is given here, which depends on the permittivity of the solvent and on the ionic concentration and the valencies. From this theory, you can also predict the capacitance of the interface, which is given here. And the capacitance depends again on the permittivity of the solvent, and it's inversely proportional to this Debye screening length, which typically for a 0.1 mole per liter solution of monovalent ions in water at ambient temperature is about 1 nanometer. Now, there have been many theoretical developments to improve this canonical description, in particular to account for correlations between ions, and in particular due to their finite size. You can look, for example, at various works, including that of Alexei Kornichev, but there are other approaches to deal with that problem. And what I would like to discuss today are the contributions, or some contributions, of these classical molecular dynamics simulations to understand the interfacial structure, dynamics, and thermodynamics. So one reason that we want to use classical molecular simulations instead of ab initio is that in order to sample the phase space of the system, and we need to consider large enough systems, especially if we want to consider phase transitions, the dynamics of charging in supercapacitors and so on. So you have to deal with thousands of atoms, and you want to simulate them for trajectories that are at least tens of nanoseconds. And this is quite difficult to reach in ab initio molecular dynamics simulations. You want to sample systems in which you fix the electrode potential, and also impose global electrode neutrality of your system. And so you also have to work out the details of the statistical ensemble in which you do the simulations, and I'll get back to that later on. But a very important aspect that you need to consider is the polarization of the metal by the external charge distribution, which consists of your electrolytes, so ions and the water or other solvent molecules. And there are several ways of accounting for this electronic response in classical molecular simulations. You have some examples here that are discussed in this recent review. And I'm going to show you some results of simulations that we do in our groups that are based on this fluctuating charge model of the electrode. So in a nutshell, the way this works is to assign to all the electrode atoms a charge which has a Gaussian distribution, because it's not completely localized on the position of the electrode atoms. It's rather diffuse inside the metal. And so here is an example of a molecular simulation box where you have two electrodes. You have one potential value for one of the electrodes, another potential value for the other electrode. You have the electrolyte in between. So in that particular case, it's water and ions as the blue dots. You can see here, for example, that you have specific organization of water at the interface with a few molecular layers, and then something that is more liquid-like. And the way the charge fluctuates is that at each time step of the molecular simulation, you recompute the partial charges, so the magnitude of each electrode atom charge. You recompute it in order to enforce the constant potential and global electron neutrality constraints. And this involves minimizing the energy under that constraint with respect to the set Q of all the partial charges of the electrode atoms. And this energy here contains both non-electrostatic interactions, which do not depend on the partial charges, and also electrostatic interactions, which contain electrolyte-electrolyte interactions. So again, it does not depend on the electrode atom charges. It contains electrode-electrode interactions, which is quadratic in the partial charges, and it involves a matrix A0 here, which depends only on the atomic position of the electrode atoms and on the Gaussian widths around each atom. And the last term here couples the electrode atoms with the electrolyte. I'm not going to give you many details, but if you're interested, you can look at this paper in the Journal of Open Source Software that describes the metal walls code that is developed in our lab, especially by my colleague Mathieu Salan. So what I would like to emphasize today is rather the fact that you can learn a lot by analyzing the charge distribution inside the electrode. And as you will see, many of the properties of the interface are related to this charge on the electrode atom. So here you have two snapshots from two different simulations. One is an interface between a graphite electrode and an organic electrolyte with these butyl methyl imidazolium cations, hexafluorophosphate anion, and in that case acetonitrile solvent molecules. And here you have water on a platinum electrode. And for example, you can see that the local charge below each water molecule depends on the local orientation. So here you have water molecules with an OH bond pointing towards the surface, and the local charge is negative, whereas below the water molecules that lie flat on the surface, because they are involved in a hydrogen bond network with other molecules, then the local charge below the water molecule is slightly positive. And so the electrode charge, the individual one, but also the total charge of the electrode is correlated with electrolyte configurations and probably with all the observables that you can compute. So any observable that is related to the configuration of your electrolyte, that could be density profiles, molecular orientations, number of absorbed ions, and so on. And as I've mentioned earlier, you can work out the statistical mechanics of this constant potential ensemble to make a number of predictions. And in particular, we showed that by sampling the joint distribution of the electrode charge with the observable of interest for various potentials, you can use standard reweighting techniques to optimally predict the evolution of the observable as a function of voltage. And we also derived fluctuation dissipation for the capacitance, so the differential capacitance, which is a derivative of the average charge of the electrode with respect to voltage. It is in fact equal to the variance of the charge distribution. So you look at the equilibrium charge fluctuations, take the distribution and its variance, and multiply by beta, which is the inverse of the thermal energy. And this gives you a measure of the differential capacitance. And we've used that to investigate structural transitions in ionic liquids. So here is the same capacitor as I've already mentioned with the graphite electrode and the ionic liquids modeled with a coarse grain electrolyte. And here is the differential capacitance as a function of voltage. And you see that there are many features. And for example, we could show that this first peak in the differential capacitance is associated with an order-disorder transition in the first adsorbed ionic liquid layer. More recently, we've moved to other types of capacitors. For example, one based on gold electrodes, model gold electrodes, and water molecules. And here is again the differential capacitance, now as a function of the distance between the two electrodes. And you see that it decreases, so don't worry about the details between red and blue, but the histograms are the results from molecular simulations. It decreases as you increase the distance between the electrodes, as predicted by continuum theory, which is a dashed green line. So the continuum theory tells you that it decays as 1 over the distance between the electrodes with the permittivity here of the liquid. But in fact, you see that there is qualitatively the same decrease, but it's far off. And this has to do with the fact that there is a difference between considering bulk and confined water. Not so much that the response of the confined liquid is different, but that there is subtlety related to how to define the width of the liquid slab here. And in order to do that, you can introduce what Netz and co-workers named the dielectric dividing surface, which you can define from profiles of the permittivity, which I'm not going to describe. And this allows you to map your density and permittivity profiles at the interface into a equivalent sharp interface between vacuum and a bulk liquid. And this corresponds to capacitors in series. So you have vacuum between the first electrode atom plane and this dielectric dividing surface, and then you have bulk water and then another DDS on the other side. And this allows you to define an effective width of the liquid slab. And if you now use the same prediction but with distance correctly defined, then you get to this black prediction, which is in much better agreement with the simulation results. Very recently, we extended this linear response with fluctuation dissipation for the capacitance to the frequency-dependent response. So this corresponds to the linear response of the current, which is a derivative of the electrode charge, to a small oscillatory voltage applied between the two electrodes. And if you remember your lectures in electronics, this response is characterized by the frequency-dependent admittance, or its inverse, the frequency-dependent impedance, which is usually a complex number. And for a resistor, it's independent of frequency, it's just a resistance. So the impedance is just a resistance. For a capacitor, it's 1 over I omega times the capacitance, and so on. And it's very related to what people measure in spectroscopy, and in particular for the lower, so the spectroscopy could be at very high frequency, what Misha told us about, but at a lower frequency, it's called dielectric spectroscopy, especially if you want to probe the effect of ions and the conductivity of ions, and how solvent and the solvent dynamics around ions, and how ions move with respect to each other, and so on. So the goal is to make predictions for the impedance and admittance, and correlate that with the microscopic mechanisms that are also measured experimentally, or at least to be able to interpret experiments based on the molecular information we extract from these molecular simulations. And so we derived a linear response expression for the admittance, frequency-dependent admittance. So it involves, again, the variance of the charge of the electrode, but also the dynamics via the charge autocorrelation function. And so this formula tells you that the impedance and the frequency-dependent admittance are related to the dynamics of the equilibrium charge fluctuations. And here you have some examples of this charge autocorrelation function as a function of time for the same system here, but with various distances between the electrodes. So you see that the initial value and the decay time depend on the distance. You can also link the charge autocorrelation function to the dynamics of the liquid dipole. So if you consider the total dipole of the confined liquid, it's actually directly related to the dynamics of the charge. And so there is a connection between what you measure with the electrode charge and the orientation of the liquid. We could also check again that there is a scaling relation with the slab widths correctly defined with the electric dividing surfaces, and this is plotted here. So this is a frequency-dependent admittance, its magnitude as a function of frequency, which is called the Bode plot. And you see that if you rescale properly by this effective widths, you rescale all the high-frequency features, which the main peak corresponds to water libration. But there is some difference at lower frequency, and at lower frequency it corresponds to what is called the Debye mode, which Misha also referred to. And this Debye mode has a characteristic time which depends on the distance between the electrodes. We can extrapolate this characteristic time using, again, this continuous picture with the effective width of the liquid slab. And the extrapolated value is about 9 picoseconds, which is the one you measure for bulk, for the Debye mode in the bulk. You can also analyze your impedance in terms of what is called the Nyquist plot, so the complex impedance in the complex plane, so imaginary part of the function of real part parameterized by the frequency. And this allows us to make the connection with the equivalent circuit models that are used by electrochemists. Of course, the case of pure water is interesting, but there are essential features that we miss with the kind of models that we use that are related, for example, to Grote's mechanism and proton transfers that were discussed by Misha. But there are interesting features that are associated with the presence of ions that we are now investigating, and in particular at lower frequencies. So I'm not going to describe that, but you really have a tool now to correlate the electric response, a frequency-dependent electric response to microscopic mechanisms, both for charge transport in the bulk liquid, but also for what happens at the interface. So now in the last few minutes, I will discuss another aspect which are already referred to in the introduction, which is the fact that electrodes are not always perfect metal, and how to capture the effect of screening inside the metal, this Thomas Fermi model which tunes the penetration of the potential the decay of the potential and of the charge distribution inside the metal, how to introduce that in molecular simulations in order to investigate the interfacial properties. And there have been several attempts to do that, and one particularly interesting one is from Lydéric and co-workers, where they used a fluid to represent the charge distribution inside the metal. So these two regions here represent the charge distribution inside the metal, and here is the confined fluid. What we tried to do is to find a way to incorporate this Thomas Fermi model in the model of fluctuating charges for the electrodes. And in fact, you can do this by coming back to the origin of the Thomas Fermi model, which is to include the kinetic energy of the electron gas based on the local density, electronic density, and using some approximations that I'm not going to describe now, you can show that the total energy now contains a new term. It has exactly the same form as before as a function of the partial charges of the electrode atom, but now the matrix for the electrode-electrode coupling includes the same matrix as before, but has an additional term on the diagonal, which involves this Thomas Fermi screening length, LTF, also the local atomic density inside the electrode. And this Thomas Fermi screening length depends on the atomic number of your electrode atoms and again on the atomic density. And the good news is that this additional feature of the model comes at no additional cost, because you can use exactly the same algorithm as before to include the metallic character in your algorithm. So what is the effect of the Thomas Fermi length on the charge induced here by lithium ion on a graphite electrode? So the color indicates the charge distribution. The darker color is a high local charge, and it fades away as you go away from the ion. If you increase the Thomas Fermi length from the perfect metal case to a finite value, then the charge distribution spreads both laterally and also as you go deeper and deeper into the electrode. And this decay inside the electrode, you can see better here for the charge induced in an empty capacitor when you apply a voltage. So the bottom panel here represents the average charge or the charge of each atomic plane as you go further into the electrode for various values of the screening length. And so the charge indeed decays with this model exponentially with decay length, which is the expected Thomas Fermi screening length. This exponential decay you also find in capacitors where you have an electrolyte. So here now it's on the potential on a linear scale across the cell. So you impose a voltage between the two sides of your electrochemical cell. You have some features inside the fluid, so no field, so no slope of the potential in the bulk of your liquid. You have some features at the interfaces that are related to the layering of water, and you do have the exponential decay of the potential inside the metal as expected. And in terms of capacitance, you can interpret that as people usually do with equivalent circuit models, with one capacitor corresponding to the perfect metal case, and two capacitors in series corresponding to the part inside the two metals. So people usually refer to a quantum capacitance because it's related to the electronic response of the metal. And so if you compare now the results from the full Thomas Fermi simulations, which are in red, with this equivalent circuit approximation, you see that you have qualitatively the good trends, but you miss quantitatively some features that are related to the coupling between the metal and the interface. In terms of the liquid structure and dynamics, I'm not going to describe that in detail, but you can look, for example, at the distribution of the orientation of water molecules at the surface, or you can look at the charge autocorrelation function and how it depends on the Thomas Fermi length. The bottom line is that all the properties of these distributions or time correlation functions can be explained by the fact that the charge induced by the electrolyte inside the metal is less localized, and this weakens liquid-solid interactions. And so this has an influence on the structure and dynamics. And I will conclude with an illustration of the effect of this Thomas Fermi screening on the interfacial thermodynamics. To start, I would like to consider contact angle measurements, or at least measurements in our simulations, but how the contact angle between a drop of electrolyte changes when you change the metallic character of your solid. And so here we have a drop of a liquid. We let it evolve for some time. We can measure the average shape. Here you have a top view where only a fraction of the liquid is shown, so that you can see that the local charge on the metal is associated with the local structure of the liquid, which you don't see, but you can guess. And so depending on the orientation of water and the presence of ions really in contact with the liquid, you have different local charges in the metallic case. In the insulating case, of course, you do not have this polarization of the metal, and this has an influence on the contact angle, which decreases by about 5 degrees from insulator to metal, which means that the metal is slightly more hydrophilic. And you can translate this change in contact angle in a change in the interfacial free energy between the liquid and the wall, thanks to the Young equation. And the associated change in the liquid wall surface tension is it's a decrease by about 6 millojoules per square meter, which may not mean a lot to you, but that's a decrease when you switch from insulating to metal. And what you can compare it with is interfacial tension at the water-air interface, which is a very high surface tension. And so this decrease is about a tenth of this number, which is considered as a very high interfacial tension. So it is significant. In order to compute the free energy in molecular simulations, it's quite expensive, and you have to resort to special tricks. And what we propose is a new thermodynamic integration method to compute this free energy change as a function of the Thomas Fermi length. And so we obtain an expression here, which is in fact very simple in terms of the charge of the individual electrode atoms. So what you need to do is simply measure the local charge on each atom, take the square, make the sum over all atoms, and this is this quantity that you then need to integrate as a function of Thomas Fermi length. And what is important is that it correlates the interfacial free energy with the localization of charge within the electrode. So here is, again, for this gold aqueous solution electrolyte capacitors, this is the integrand, and this is the free energy as a function of the Thomas Fermi length. So the symbols are simulation results of this Thomas Fermi thermodynamic integration. The line is a fit, which is inspired by the models that I'm going to describe on the next slide. But the important thing is that when you go from LTF equals 0, which corresponds to the perfect metal, to LTF equals infinity, which corresponds to the insulator case, we obtain an extrapolated value which is consistent with what we estimate from the contact angles, which is the dashed line here with the arrow bars as a shaded area. And what this formula tells you, so is that the interfacial free energy is related to how the charge is localized in the metal, and we could propose a model based on an expression for this local charge on each atom. So it contains several terms. One, which is the effect of the average charge, and because the charge scales linearly with voltage, so this contribution to the free energy is quadratic in voltage. It involves the integral charge. And then there is another term which comes from the charge fluctuations. This is why it involves the thermal energy kBT. It depends on the differential capacitance, which, as I've mentioned already, decreases with the Thomas Fermi length. It also involves a correlation length, which tells you the extent of the charge domains. And as you can see here on this snapshot, it depends on the value of the LTF. And generally, the correlation area increases when you increase the screening length, as you might expect. And there is a last term in the model which comes from the decay of the potential as you go deeper and deeper into the solid. And this involves the exponential decay and the fact that you have discrete atom planes that are separated by some characteristics. Length A, which is related to the lattice of the metal. And all this work shows that charge correlations within the electrode play an essential role on the interfacial thermodynamics. So with that, I would like to conclude. So using these molecular simulations and combining the statistical physics tools of the constant potential ensemble and the fact that you can tune the metallic character of the electrode, we could investigate the interfacial structure, dynamics, and thermodynamics of a variety of electrode-electrolyte interfaces. And if you're interested, you can have a look at these two complementary reviews that I already mentioned. I would say just a few words about work in progress in order to improve the description of the interface. And it's in fact already possible to also consider a polarizable electrolyte. You just need to consider self-consistently the induced charges in the metal and the induced dipoles in the electrolyte. You can capture some aspect of chemical reactivity already with these simple models, focusing on the solvent contribution to redox processes, as in Marcus theory. And we are making effort, and especially my colleague Guillaume Jean Méret, to have improved implicit solvent description compared to simply having a continuous medium with a permittivity, especially based on molecular density functional theory. And of course, there are many challenges for the field for molecular simulations in this context, and several have been already mentioned by Misha. A very important one, which we miss at this stage, is chemical reactivity in order to go beyond the solvent contribution to redox reactions, and in particular bond dissociation, proton transfer, and so on. So there are very interesting research projects in that direction in various groups. For porous electrolytes, there is also the issue of the flexibility of the matrix, which may play an important role. And this has already been mentioned, the electronic response may in some cases play a very important role, especially on the dynamics, and so we have to include a description of the properties of the metal beyond Born-Oppenheimer, and I'm very glad that these three authors are in the room, and Angelos is also there. So there are also very interesting directions to take in this field. I will conclude with acknowledging a number of collaborators, especially Mathieu Salan, in the Phenix lab, with whom a large fraction of this research is done. The first part on the frequency-dependent impedance is work of the postdoc of Giovanni Piredu, and the second part on interfacial thermodynamics with Thomas Vermeer screening is the work of Laura Scalfi's PhD. And with that, I would like to thank you for your attention.